All right, so let's go back to these different types of thermodynamic processes and fill in some of the, oh yes.
Yeah, I have one question. Why is it just on the inside and not the whole area underneath?
Oh, that. So it's because you see how there's three, like you could put dots here and here.
Oh,
so you want to integrate from here to here, and then you integrate from here to here, and you add them together. But this one should be positive. This one will be negative because you're going the other direction. So when you subtract them, it just gives you what's inside.
Oh, I see. Okay.
Yeah. So like that's what that visual looks like. So you integrate this way, and then you integrate that way. When you add those together, it's always going to be just the stuff inside the loop. Okay? Yeah. Yeah. I animated it. So an isochoric process, that means constant volume. Okay? If we want to figure out the different points from here to here, we can use our PV equals nRT relationship. We know that volume stays the same, N stays the same, and R stays the same. So the only variables we need to worry about are P and T. So that means P1 over T1. So if you know the pressure and temperature here, and you know either the pressure or the temperature here, you can calculate what you're missing. Okay, so to go from here to here, you use this. All right, what do we know about the work? What's the work here?
0.
0, right? The integral of this is 0. Okay, so the work's 0, which means change in thermal energy is equal to Q, equal to the heat. All right, how do we calculate the heat for a constant volume process? We talked about this a little bit, but we'll go into more detail later. Heat for a constant volume process is NCV delta T. Remember, this is like MC delta T, but for gases. Okay, this is for ideal gases. So for ideal gases, you can calculate heat for a constant volume process, and you can calculate heat for a constant pressure process. If it were constant pressure, this would just be Cp delta T. It's a different constant. Yes.
The C and VCP stuff's going to be given, right?
Yeah. Or at least it'll tell you if it's a monatomic or diatomic gas, because remember you can calculate that by figuring out the degrees of freedom. Right. You can write that down, right? There's only 2 numbers you have to know, but it'll probably be given.
And that's for a constant what?
Constant volume. Okay, so that's specific to a process like this. So Q is NCV delta T if it's a constant volume process. Okay, so now you can calculate all the things, right? All of the things that you need to do the first law, because we know Q is this. We know if Q is this, then so is change in thermal energy. And we know work is 0. Okay? All right, let's talk about an isobaric process. That is constant pressure. So if you want to if you know stuff about this point, right, you only need to know V and T to go back and forth between that point and that point. So remember, we have PV over T between all of our points. We can get rid of P because we know P is the same. Okay, so this is V1 over T1 is equal to V2 over T2. That's a good way to figure out what's going on between those two things. What's the work here?
The integral.
But how do you get, like, it's pressure. It's base, which is delta V, times height, which is P. So P delta V. Okay, work done by the system should be P delta V. In this case, is it positive or negative? Positive. Work done by the system here is positive. Work done by the environment would be negative. Okay? So, we use this. We can't get rid of any of these things. None of these things are 0 for an isobaric process. So this is Q minus work system. But what's Q if we have a constant pressure process? Yeah, NCP delta T. Okay? And it turns out thermal energy always, always, always is NCV delta T. So even if it's not a constant volume process, this is still true. Okay, so you can figure out all of these things. Here's how you figure out work. Here's how you figure out heat. Here's how you figure out change in thermal energy.
So that's always true for thermal energy?
Yeah, this is always true. for any process, not just constant volume or constant pressure, for isothermal, for any random process that's not one of these specific stated things, okay? Yeah. All right. So these slides are very important. You should probably write down the stuff on these slides on your cheat sheet, okay? Isothermal process, that is constant temperature, all right? So if we want to go back and forth between this point and this point, we know P1V1 is equal to P2V2 because we can get rid of the temperature part. How do we figure out the work? What's the work going to be? It's the area under the curve, but let's talk about what that actually looks like. So, we know work is going to be P dV. Okay? If we know that we have PV equals nRT, we want pressure in terms of volume. So pressure becomes nRT over volume. But what do we know about nRT in this case? Does n change? Does T change? And R is a constant. So that whole thing is constant. Okay, so when you plug this in, this becomes nRT over V dV. If you take this out, nRT comes out, and you end up with dV over V. Okay, what does this integral give you? And this goes from V1 to V2. What's the integral of 1 over x? Yeah, ln, natural log, right? So this becomes nRT, natural log of V from V1 to V2. Okay, so that goes together. So that is our work. Okay, nRT, natural log of V from V final to V initial. Okay. What do we know about change in thermal energy for a process like this? 0, right? Temperature doesn't change, so thermal energy doesn't change, and the change in thermal energy is 0. Oops. So that means our Q is equal to our work. So even though we don't have a specific Q, right? Because remember, the Q's we can calculate are constant volume and constant pressure. So we can't easily calculate Q here independently, but we know it has to be equal to this. All right? Okay. I think we'll go through this one together.
So as always with this problem, this is a problem on thermodynamic processes and work. I'd like you to try it yourself before following along with my solution. But if you're going to try it yourself, here's a good place to pause. And I'm going to get started. So just to start out with, we want to draw a PV diagram for both of these and sort of decide whether the work is positive or negative, okay? And so the way that we decide if it's positive or negative is we're looking at whether we're basically going to have to decide if it's work done by the system or on the system. If we're talking about work done by the system, then it's definitely positive because these are both expansions, so the gas is pushing out, okay? All right, so we're going to draw the PV diagram. This is pressure, this is volume. We don't actually have units here, but we could use units, so we probably want kilopascals, which is 10 to the third pascals up here, and meters cubed down here. We're going to start with volume 1, and then there's volume 2, and then we have pressure 1, and we have pressure 2. So volume 1, volume 2, pressure 1, pressure 2. So starting with process A, all right, so we'll pick a color here. We'll make process A green. So process A, that means we have 1 mole of gas at standard temperature and pressure is isobarically expanded to twice its volume. So let's say this is our STP, so that means we know what our volume is from the example in the last chapter where we calculated 1 mole volume at STP. We'll go into that in a minute. So we're starting here, and we isobarically expand, so that means constant pressure to twice the volume. So you could call this, oops, 2V1, and this is moving in this direction because we're going from a smaller volume to a bigger volume. That is an expansion. Okay, so here's our points. For process B, we're looking at the same gas, so we start at the same spot, okay, down here. It undergoes an isochoric process, that means constant volume, during which the pressure is doubled. So we want to go up to this pressure using an isochoric process. Oops, that's not great. Let's try this. Okay, there's our isochoric process. And then it undergoes an isothermal expansion during which the volume is doubled and the pressure returns to its initial value. So that would be down here, the same spot as we did this other thing. And you have this inverse curve that looks like this. So we have process B in orange, and we have process A in green. And so now we know where everything is. So this, we always start here. This one goes up here and then down to the original spot. So we start and end at the same points. And that's important because we're going to see that even though we start and end at the same state, we're going to end up with different values. So because we're talking about work done by the system, that's the work done by the gas. So that's going to be positive work. So that's just to check our answer later, okay? And we also know that we can figure out our initial pressure, volume, and temperature. So remember, we have N equals 1 mole, and at 0.1, we have pressure 1, which is 101.3, but well, we'll just skip that, times 10 to the third pascals. We have temperature 1, which is 273 Kelvin, and we have volume 1, which you can go back to example 1 in the last chapter if you're not sure how to do that, but you just get it from PV equals nRT, and that's going to be 0.0224 meters cubed. So you could write that in here. We know this is 0.0224, and this would be 0.0448. So you don't have to do a lot of calculating there. This one's also equal to 2P1. So if this is 101 kilopascals, this is 202 kilopascals. So now we have all of our values, okay? So P1, P2. To calculate the work, we need to use our work formula. So for A, process A, calculating the work is relatively straightforward. We just look at the area under the curve, and that's going to be this area. Oh, weird. Sorry. I'm gonna change that. Okay, that's this area. Okay, so that area we'll call work from area A, and you can see it's just, you know, if we consider this P dV, right? That means it's pretty straightforward. It's just a rectangle, so it's going to be equal to pressure times your change in volume, and that's going to be pressure 1 times your change in volume, which is going to be equal to V2 minus V1. So that gives us pressure of 101 times 10 to the third pascals. Our volume is going to be basically 0.0224, and that's meters cubed. So you plug that in, and you're going to get 2,270 joules. We're keeping our 3 sig figs because that is the values we're given. We used all 3 sig fig values, and you don't have to do that, but it just seems to be working for what we want. Okay, so that's our first area. Our next area is a little bit more complicated. That means we have to we're really just calculating the area under this isotherm. But remember, we go all the way down. So this is our other area. And to do that, we are going to have to use the area for the isotherm. So work B is actually 0 because remember this section is isochoric, so it doesn't have an area under it, plus the area under the isotherm. So there's a couple different ways to do this, but the easiest one would be, it's actually just nRT V final over V initial, or PV, remember PV equals nRT, so if you have nRT and it's constant, it's the same as P1 V1, it's the same as P2 V2, so whether you use this point or this point, it actually doesn't matter because P times V is going to be the same all the way along the isotherm. That's how PV equals nRT works. So we're going to call this P1 V1 natural log, and that's V final over V initial, but we know V final is just twice V initial, so 2 V1 over V1, which just ends up being 2. So this whole thing gives us, just 101 times 10 to the third pascals. Our volume, initial volume is 0.224 meters cubed. And then we have natural log of 2 because as you can see, V1's cancel here. So you plug all that in, and it should give you something a little bit bigger than the last one, so 3,140 joules. That makes sense just looking at this because you can see that this area should be bigger than the green area. So that means we have positive work for both of them, and this process B is going to do more work.
Okay, so let's talk about the thermal energy. So the internal or thermal energy of an ideal gas depends only on its temperature. So we know there's some relationship between delta T and delta ETH, okay? And it turns out this is the relationship. NCV, the C, the heat capacity for a constant volume change, times delta T. Okay, so this is the constant that connects this to this. Right? And this is always true. Remember Q, this term is true for Q for an isochoric process. But for an isochoric process, work is 0. So this is true for E thermal and for Q for an isochoric process. For something like this, for an isothermal process, right, this is true for E thermal but not for Q. Right? For an isobaric process, this is true for E thermal but not for Q. Right? So this is always true for your change in thermal energy, but it's not always true for your heat. Okay?